G'day chemistry students, in this video we're going to be looking at dot point 6.3.4, looking at dissociation, particularly of weak acids and bases in a lot more detail, looking at that equilibrium and then applying our knowledge of quantitative equilibrium, looking at equilibrium constants in particular, for this video Ka and Kb. Let's get into it. What I want to look at first are acid dissociation constants. Now we already know that if we have an acid HA and put it into water, that there is going to be a dissociation. That hydrogen on the acid is going to donate onto that water, forming hydronium and leaving the conjugate base A-, which is just an anion. Now this is an equilibrium. We've talked about before that for strong acids and bases, essentially we have 100% or near 100% dissociation, which means that we have a very big skew to the right. But for weak acids in particular, there's a mix of both. Some of the particles will be non-dissociated, some of the particles will have dissociated. As a result, we can write an equilibrium expression. Here we have our product of products and our product of reactants, noting that we don't include our water. It's a liquid, it doesn't have a concentration. Just like we've looked at before with our other equilibrium constants, here we can also acknowledge that the size of Ka, the size of the equilibrium constant, will tell us the degree of dissociation which is occurring. So for example, if I have an ammonium ion, its Ka is low relative to the rest of these weak acids. Its Ka is 5.6 times 10 to the negative 10. Because this number is so low, what that suggests is that the product concentration is low and the reactant concentration is high, meaning that there is a lower degree of dissociation compared to the other acids which are here. Of the weak acids that are here, the one which looks to have the largest rate of dissociation is the hydrofluoric acid. Its Ka value is 7.6 times 10 to the negative 4. That's the largest Ka value that we have here, suggesting that we have the highest concentration of products and the lowest concentration of reactants. If we were looking at any of these acids that were strong acids, we would expect the Ka to be significantly larger. We would have large concentrations up the top and essentially a HA value near zero. So those Ka values would be extremely large in comparison. What we can also do with Ka values is put it on a log scale, just like we've done before with our pH and pOH values. So that works in exactly the same way. We just have this value here called pKa and put that onto a log scale. What we can see is for substances with the highest Ka values, they have the lowest pKa values. And that relationship is very similar to what we saw with something like pH. Things with very low pHs had the highest hydrogen ion concentrations. Same kind of gist here. We can also apply pretty much the same concepts to base dissociation. We just need to be using our different general equation. We have a base, it interacts with water. The water is going to end up donating the proton and acting as an acid, forming BH+, its conjugate acid, and we're going to also have some hydroxide there at the end. We can write up a Kb expression. Kb value is going to work the same way that the Ka value did in terms of relative size. So for example, this phosphate ion here, its Kb value is the highest out of the group. That means that it's going to have the highest rate of dissociation because it's going to have the largest concentration of products compared to the concentration of reactants. And that'll follow the same patterns for all of the other p values that we've looked at as well. Now, dissociation constants can be helpful for a couple of reasons. We can compare dissociation constants, or pKa and pKb values, to figure out the relative strength of acids and bases. So we can look at, say, two weak acids and figure out which one is stronger when we compare the two, and that's determined by the Ka or the pKa value. We can also do more calculations similar to the ones that we've already done surrounding hydrogen ion concentration, hydroxide ion concentration, and pH and pOH. In fact, we can just add that to the flowchart that we already have. So using hydrogen ion concentration, we can apply that number to an equilibrium expression. Assuming that we have the other relevant values and concentrations, we can determine Ka. use our P equation to get to pKa. Similarly, if we have hydroxide ion concentration and we have all of the other information that exists in our equilibrium expression, we can do a Kb equation to find Kb, and then use our P equation to be able to find pKb. For the remainder of the video, I'm just going to do a couple of quick calculations to show you how that might work. So in this video, we're going to complete two calculations. One's going to be Ka related, one's going to be Kb related, keeping in mind that they work roughly the same anyway. It's just sort of being on two different ends of the flowchart that we've looked at before. In this question, we're being told that the pH of a 0.05 molar solution of nitrous acid, HNO2, is measured as 2.22, and we're being asked to determine the acid dissociation equilibrium constant. In other words, we are trying to find Ka. So let's just write down the equation for the reaction itself. We know that we're working with an acid, nitrous acid, so HNO2, that is aqueous, and it's going to be put into a solution of water, so that's what it's interacting with, H2O there. When it interacts with H2O, because it's an acid, the water will act as a base, accepting a proton. So that's going to mean that the hydrogen is going to go to the water. That's going to leave nitrite, NO2, charge of -1, and form as well hydronium ions. So when we are looking at writing up a Ka equation, it's going to look something like this. Concentration of products times the other products, so our hydronium, divided by our concentration of reactants, which in this case is just going to be the nitrous acid, not the water. It's a liquid, as always. It doesn't end up in our equation. Now, there are two things to keep in mind. Concentration of hydrogen ions is going to be the same as the concentration of hydronium, which is also going to be the same as the concentration of the nitrite, the NO2 minus. And we know this because we're reacting and producing our ions in a 1-to-1 ratio. We also know that these two guys are essentially interchangeable and mean roughly the same thing. This value is going to be attainable through calculations from pH. So knowing all that, we can simplify our equation a little bit further and say that the Ka really is the concentration of the hydrogen ions, which we're about to find from the pH, all squared, divided by the concentration of our nitrous acid. We already know the concentration of the nitrous acid. It's been given here. The only thing that we don't know is currently the hydrogen ion concentration. But we can calculate that by rearranging our pH equation. pH is equal to neg log 10 of our hydrogen ion concentration. We already know pH. We don't know H+. So what we need to do next is make H+ the subject using either our algebra or our memory. We should be able to conclude that that means that we're going to do 10 to the negative pH, which is 10 to the negative, in this case, 2.22. Putting that into our calculator, that is equal to 0.006. Again, I'm going to carry that number along as I go. At this point, we can substitute, so Ka is going to be equal to 0.006 squared, divided by the concentration of the nitrous acid, which is 0.05 molar. This will then allow us to determine Ka. That is equal to 7.3 times 10 to the negative 4. We're going to be rolling with two significant figures. That matches the number of significant figures in the concentration for nitrous acid. In the second question, we've been given information about a phosphate ion. We're being told that it's acting as a base, considering that we're being given a Ka value. That's certainly what's being implied. We need to find the pH of solution. So first thing that we should do, again, is write out an equation. So we know that we have a phosphate ion. We know that it's going to be interacting with water. We're being told that it's a base, so it should be accepting a proton from the water, which means that we are forming hydrogen phosphate and hydroxide ions. Keeping all this in mind, we see again we're reacting in a 1-to-1 ratio. That's pretty straightforward. We can then write the Kb expression next. So products first. All divided by our reactants, keeping in mind that water is a liquid, it will not be included, just like in the previous question. So it's just the phosphate ion down the bottom. Keeping in mind that we already know that phosphate ion, we've been given its concentration. The only thing that we're going to need to do is figure out these ones. Now, in this question, we're being asked to find the pH, which means that we're going to have to try and figure out either the hydrogen ion concentration, or in particular for this question, it's going to have to be the hydroxide concentration, and then we're going to have to do a conversion. So we are trying to find the hydroxide ion concentration in this question, keeping in mind as well that because of, again, our molar ratios, the concentration of hydroxide is going to be equal to the concentration of the hydrogen phosphate. So because they're equivalent, we can simplify our equation a little bit more, and that's going to be hydroxide concentration squared divided by our phosphate concentration. Once we've done that, we now need to solve for the hydroxide concentration, because that's the thing that we need to be able to calculate the pH. So let's rearrange for that. So hydroxide ion concentration squared is equal to the Kb value times the phosphate concentration. We can then square root both sides, so I'm just going to remove the square here, put the square root over the top, and then substitute in the values that we have. So we've been told that the Kb value is 5.9 times 10 to the negative 3, and we also know that the phosphate ion concentration is 0.32. All we need to do is square root the whole thing, and that will give us our hydroxide ion concentration. That should be equal to 0.043. That's just the 2 decimal places. I'm going to carry my number for the next part of the calculation too. Now that we know the hydroxide ion concentration, we should be able to go from hydroxide ion concentration to POH to pH. That's going to be my plan. So to convert to POH, excuse me, so POH is equal to negative log 10 of the hydroxide concentration. So that's negative log 10 of 0.043. So I'm going to put that into my calculator. That is equal to 1.36. Next thing that I'm going to do is convert to pH. So pH plus POH is equal to 14. pH is equal to 14 minus POH, which is 14 minus 1.36. And that is equal to 12.64. And there we go. 2 ways of using Ka and Kb. Either having enough information to actually calculate the Ka value itself, or being able to use the Ka or Kb value to be able to determine the concentration of one of your ionic parts, and then be able to do further calculations using some of the skills that we've already learnt about in this topic.